So the topic for today is application of Gauss's law. And before that, let's just do a quick recap of what was actually Gauss's law. If you remember, we did it in the last class. We discussed that. But if we just want to understand Gauss's law, one concept that we should know is the flux. Okay. So before we go to flux, let me just give you what is Gauss's law. Gauss's law states that the flux coming out of any closed surface. The term closed is very important. The surface should be more or less closed. Is nothing but 1 by epsilon naught times the charged enclosed by the surface. So what we can do is we can simply write it down as, let's say Q is the charge enclosed divided by epsilon naught. Since it is enclosed, so I can write it down as Q inside. So this is my Gauss's law. Okay, so at this side we're basically talking about the flux. So that's the basic overall statement of Gauss's law. But eventually you will see that there are a lot of applications for Gauss's law which we are going to see, and it makes a lot of problems easier. Okay, there is no such derivation for Gauss's law. There is an indirect way to prove Gauss's law that we are going to check. But let's just check and talk a bit about flux here. Okay, flux is a very simple concept. You can have any kind of surface. Okay, even you might have let's say we have a charge q and it is enclosed in a circular or spherical surface. Let's consider a three-dimensional picture and it is enclosed in a spherical surface. Whenever we are going to consider any surface area, let me say this is a very small surface area that we are considering, and let's say this is dA. So the direction of this area, because this area is nothing but an area vector, so this direction of this area is always perpendicular. Please remember, the direction of the area vector is always perpendicular to the surface. So in general, if you are basically having an area like this concept is very important to solve any numerical problem. The direction of the area vector will always be perpendicular to this. So that's the direction of the area vector. In such scenario, because it's a positive charge, the electric field will be coming out of the positive charge. It won't go towards. This will also be coming out in the same direction as the area. So that means the angle between the charge and the area is 0 degree in this case. Okay, but in case, let's say the electric field is in one direction, let's say this is E. Okay, I'm just giving a general statement, and the area might be in some other direction, dA, and maybe the angle between them is theta. Then this flux that we are talking about is given by E vector dot dA vector. Now if we take the dot product of two vectors, we know it is nothing but E dA cos of theta. But as we keep on solving our problems, we will see that mostly for all our problems, theta would be either 0 degree or 90 degree. Okay, so if we just look from here, what can we write down for Gauss's law? This states that the Gauss's law can be written in a different way as well. Flux, which we know is nothing but the flux of the closed surface, which is this closed surface, is equal to E dot dA. We can simply write it down as E dot dA is equal to Q inside by epsilon naught. Okay, so that's my since it is a small area, so I can say we're talking about a small flux. Okay, if you want to find out the total flux, that means phi closed total flux, that means we have to integrate this. We can simply write it down as integration of d phi. Closed means we are going to take a closed integral, that means this side also we have to integrate e bar dot dA. Okay, and as per Gauss's statement this must be equal to q by epsilon naught. Anyway, we are going to solve problems based on this, and these things will become more and more clear. Okay, so that's very important. One more thing I'd like to discuss, which we have already discussed before, but I think it's important because we are going to need it now. because its syllabus does mention this part. There are three kinds of charge density. One is the linear charge density. Okay, this is all revision. We already know it. We usually denote it by lambda, and this is nothing but charge per unit length, right? On the other hand, we can also talk about a term which is called surface charge density. Hopefully, we'll be able to cover these topics today. And this is we can write it down as sorry, we can write it down as sigma. Surface charge density is nothing but q charge divided by area. Okay, and then finally we can also have the third thing, which is volume charge density. It is rho is equal to q divided by v. So these are the three kinds of charge density that we have. Now let's try to solve certain problems and check for Gauss's law. Okay, and the Gauss's law, the concept is not very complicated. We can actually do that. Okay, so let me just start with something very simple. Okay, or maybe we can think about it in this way. This is just an example that we can take up. Let's say I want to find out the flux through a hemisphere. Okay, flux through a hemisphere, or maybe flux to a sphere. Let's try to find out the flux through a sphere. So I have got this charge is q. Okay, and let's say we have a sphere which is circling this charge. Okay, now always remember, whenever we want to use the Gauss's law, we have to consider a closed surface. That closed surface may be an imaginary surface, and that is actually called the Gaussian surface. That's a technique to solve uh, the system for electric field. If you want to find out the electric field, we have to construct a Gaussian surface around this. So we know that the Gaussian surface is this, and let's say that the radius of this Gaussian surface is r. Okay, now if we go by the statement of flux, okay, we know that phi is equal to E dot A. But let's say I'm considering a very small area, which is dA. So I can simply write it down as E dot dA, and let's say this is my d phi. Okay, so that means if I consider this, and we know area and field will have the same angle, 0 degree, so I can simply write it down as E dA cos of 0 degree. So this is E d. So this is the definition, and by this we get that this is the flux coming out of a very small area dA. Okay, now before we proceed, we can actually think about it in this way also. See, this is one area. We can consider a number of areas here. One area is here, one area is here, one area is here, one area is here, and so on for the entire circle so that it will cover all the areas. So that means if I want to find out the total flux, I will take this, I will integrate this. So my total flux phi is equal to, now the electric field is uniform. See, whether you take this small area, this small area, this small area, in all the directions, the electric field is uniform. The Gauss's law, it's important that we consider that at this point of time we are considering a uniform field. So let's say this is the uniform field. I will take it to be E and integration of dA. Now you see it's forming a closed surface. So maybe I can talk about the entire surface area. Now this is a sphere. This is a three-dimensional picture. So if you're considering a circle, we know area is pi r square. And if you're considering a sphere, we know that the area is 4 pi r square, where r is the radius of this. Okay, so this is simple. Now I will consider one more thing also. We know by definition what is electric field. We have already done it in the first part, and by definition the electric field is K, okay, whatever is the charge divided by r square, right? This is a uniform distribution of field. That means whether you be here or when you are considering and finding out the electric field here, that means the distance is r, and we know that this electric field at this particular point would be nothing but kq divided by r square. Okay, so what we can do now is we can actually replace it here, and if we replace it, we get that the flux is equal to E. In place of E, I can write down as K, which is nothing but 1 by 4 pi epsilon naught into Q divided by R square is equal to, into, sorry, this place of E we have written KQ square, and then 4 pi R square, 4 pi R square. So let's see, this R square and this R square gets cancelled. This 4 pi when this 4 pi gets cancelled, I'll get it to be q divided by epsilon naught. That is my phi, which is nothing but flux. And obviously this is for the closed surface because we've integrated for the entire area. So this is for the closed surface. And this is obviously my Gauss's law. So this actually in a way tells me about the Gauss's law, the proof, which is actually no, just an application, not a direct proof. It's basically an indirect proof here. But this particular thing that we have done tells me a lot of things, a lot of important points regarding Gauss's law. Okay, let's just write down some important points. Number one, uh, we have always, in order to use the Gauss's law, you always have to consider constructing and surface. Okay, or we can write it down a Gaussian surface around the charge, around the charge. In that way you can find out what is the electric field very easily. But please remember that this surface that you are considering should be symmetric. That's actually one of the restrictions as well in Gauss's law. It should be symmetric. So if you have a charge here, you cannot draw a surface like this. Then won't be symmetric because it will be at a different distance from this end, it will be at a different distance on this end. It has to be at the same distance on all the ends. And that is actually a very important point that we should note when we are actually doing it for the Gaussian surface. Okay, just a moment. So as I said that this Gaussian surface we should always consider in such a way that it should enclose that charge. That's very important. Okay. So let's take one example, very simple example. The question is you have to find out the flux through a hemisphere. So if you have a sphere and if you cut it into half, you're basically going to have a hemisphere. Okay, so let's say you are having a charge. This will actually clear your concept of what do I mean by symmetric. Okay, you have a charge here. You have to find out the flux through the hemisphere. So what you can do is we can actually draw a hemisphere. Okay, maybe this is my hemisphere, but the problem is this charge is not having a symmetrical distribution. It is on one edge of the hemisphere. So what we have to do is we have to make an imaginary other part of the hemisphere. So let's say we are doing it like this. Now this is an entire sphere. Okay, so that means if we are considering the flux, okay, through the sphere, okay, if we have a sphere as per the definition of Gauss's law, it will be q by epsilon naught, because whatever is the charge inside, it is enclosing, and this is q by epsilon naught. Okay, it doesn't depend on anything else. If we are talking about hemisphere, that means half. So understand this. Flux means you'll have the lines of force going like this, like this, like this, like this, like this, and so on. Correct. So if it's in the center, half of it will go in this direction, half of it will come in this direction. So that means if you want to find out what is the flux through the hemisphere, okay, this is definitely going to be half of q by epsilon. Okay, so these kind of questions you can actually think about the problem and try to solve it, and that will make it very easy. Okay, there are a lot of different kinds of problems you might get here. For example, let me take one more example here. Let's say I basically got a cube. Okay, so I hope you know what's a cube. We are just considering 3D picture here. Okay, so you need to have your imagination power a bit stronger sometimes. Okay, so I'm just drawing a cube here. Okay, and a cube basically will have 8 sides, 8 edges, and so on. Okay, so this is my cube. This is my cube. Okay, so in general we did it in the last class that if you're basically having a charge here. Okay, if you're basically having a charge here at the center and you want to know what is the flux, it is obviously q divided by epsilon, because that is the charge being enclosed. It does not depend on the shape. Okay, but on the other hand, if we just want to find out what is the flux through one phase, we know it's symmetrical. There are one, two, three, four, five, 6 phases. So that means through one phase, okay, phase one, let's say, it will always be q divided by 6 epsilon naught. Okay, so this is a very important point and a conclusion, because it tells me that uh, flux, okay, the flux that we're talking about phi does not depend on shape. We can see that from this problem. See, this is q by epsilon naught. Previous problem, it was again q by epsilon naught. Whether be it a circle, semicircle, maybe a cube, and so on. Okay, it does not depend on the shape. It just depends on where the charge is exactly placed, how much is the symmetry. Those are the important points. Okay, so this is one more thing that we should remember, but I'm not going to discuss this because this is something which is very obvious. I will make this thing a bit more complicated, and I will say that, let's say this charge is not at the center. It is not at the center. Let me rub this face numbers. This is not at the center. Rather, this charge that we are talking about is placed somewhere here. Q is here. Now, the problem is that it is not symmetrically distributed, because I am not having this charge at the center of the cube. It is at the edge of the cube. The question is, how much flux will pass through this cube? Okay, flux through the cube. Okay, so the question might be flux through the cube with charge at edge. Okay, through the cube with charge at edge. At edge. So we have the charge at the edge. Now the problem is I don't have it in a symmetrical distribution, but I can construct an imaginary Gaussian surface. So this is at one edge. So imagine I can construct one cube here. Okay, I can always construct one cube here, something like this. Okay, and then in a similar way I can construct one cube on this side, and so on. Okay, and then I can also construct one cube at the bottom. Now you have to have a very strong imaginative power. I cannot draw that 3D picture here. So I have drawn 3 cubes on the back side. Similarly, I also have to draw 3 cubes on the front side. Okay. So now imagine that if I want to draw a symmetric structure with the charge at the center, I have to draw 7 cubes around it. One cube is already on one edge side. I have to draw 7 more cubes. If we are considering a three-dimensional picture, that means you have to draw 8 cubes. Okay, so the simple thing would be, you don't have to write down anything here. You have to just understand that what exactly we have to do so that we are able to solve it. Okay, draw 8 cubes. Okay, so if we draw 8 cubes around this charge q, around q, to make it symmetric, make it symmetric. Okay, so that means I'm considering the total flux that is going out through all the 8 cubes. Okay, the total flux going out through all the 8 cubes That's obviously as per Gauss's law, Q divided by epsilon naught. But the question says, what is the flux coming out of this cube? This is 1/8 of the total Gaussian surface that we have. So the flux coming out through one cube would be equal to Q divided by 8 epsilon naught. So this particular problem tells me that it is all about being symmetric in nature. If it is symmetric, we can easily say that how will the nature be. So that's very important. Okay. So we have to construct it in such a way so that it becomes symmetric. Okay. Let me take one more example. All these examples are important, and if you get this, this is slightly tricky. Let's say I'm considering a cone now. Cone. So cone, I hope you understand. You have the solid angle there, ice cream cone rather. Okay. So if you want to construct a cone, what we can do is we can take one line like this, and maybe one line like this. Okay. And then we can actually have this. Okay. And let's say we have the charge here, Q. Now again, so you have to have a bit of imaginative power. It has to be a bit of imagination important. We have the Q here. Now you want to bring it exactly at the center of a symmetric structure. So what you can do is you can construct one cone on this side, one cone here, then another cone here, another cone here, and in this way you can construct a lot of cones. As a result, what you're going to get is nothing but a sphere, imaginary sphere, and that sphere is actually going to form a spherical surface. Okay, so it's a spherical surface, and that will actually give you a part of your Gaussian surface. This is my Gaussian surface for the cone, right? But I'm not going to do the derivation for that. That's a different topic. But you have to remember, using this logic, we can actually find out what is the flux that is coming out through the code. So what we can do is, you'll get some numerical problems maybe. What they will do is, they will bisect this part, okay, and tell you what is the angle here. So this angle is theta. This angle is theta. Okay. So if this angle is considered to be theta, the flux through the cone, if you want to calculate flux through cone, if you want to calculate this phi cone is equal to Q. We're not going to do the derivation. You have to remember this, divided by 2 epsilon naught into 1 minus cos of phi. Okay, try to remember this because this is important. So if you're considering a cone, and if you want to find out what is the flux, theta is let's say given, we can directly use this formula. We're not using anything different here. We are using the same logic of having a symmetric charge at the center of a sphere. Q by 2 epsilon naught 1 minus cos phi, where this is a phi. Okay. Anyway, I have denoted it as theta, so I should not write down phi. Phi we're denoting it as flux. I'll write it down as theta. Theta. That's it. So this is the one which is there. But then you can use this for solving different kinds of problems. If you know this result, you can find out different problems. Okay, and you can solve it also. Let me take one more problem. It is all about Gauss's law. If these things are clear, this will be clear. The question says you have to find out the flux through curved surface of a cylinder. So you have to find out what is the flux through the curved surface of a cylinder. Okay, so if you want to do that, what we can do here is, first we can actually draw a cylinder. Okay, and if we draw a cylinder, maybe something like this, and a cylinder would be like this. So it has got three regions. This is my top face, let's mark it as region 1. This is bottom face, let's mark it as region 2. And the rest of the part, it's a 3D image, obviously it's a cylinder. Whatever is its surface is the third space, which is the curved surface. You have to find out the flux through the curved surface of a cylinder. So that's very important. Okay. And let's say we have the charge here exactly at the center. We have the charge exactly at the center. And these things will definitely be given to you. Um, Let me just go here. The distance from here to here is r. The distance from here to here is again r. And let's say the radius of the cylinder is also r. Okay, so these are the parameters that are being provided, but you have to find out what is the flux coming out of the curved surface. If someone tells me what is the total flux, I can obviously write down phi is equal to q by epsilon naught, but I have to find out only through the curved surface. That means whatever flux is coming out through surface area 1 and whatever flux is coming out through surface area 2, I have to cancel that out. Charge is symmetric, charge is here at the center, so that means the flux that is coming out through the curved surface or the upper surface 1 and the lower surface 2 is going to form a cone. See, these two are forming a cone. Now if you form a cone and if you want to use that formula, we have to know what is the angle. So this is r, this is also r. So this is more or less forming a triangle. If these two sides are equal, this angle is going to be 45 degree. Okay, so obviously the angle is going to be 45 degree, a symmetric cone. Okay, this entire angle is going to be 90 degree and this has to be 45 degree. Okay, because this is 90, this would be 45, this would be 45, so it will basically form that triangle. So you can look into the dimensions and check that. So this is 45 degree. So we are basically having two cones here. Okay, flux, if you want to find out the flux of two cones, we can simply write it down as, for one cone it is q divided by 2 pi epsilon naught into 1 minus cos, I told you, remember this formula, theta is nothing but 45 degree. This is for one. There are two cones, same logic, into 2. So this 2 and this 2 will get cancelled out. And here cos 45 is 1 by root 2. We know it. So I'll write it down as q by epsilon naught into 1 minus 1 divided by root 2. So that's my flux that is coming out of the cone. But I need the flux coming out of the surface. Okay. So we know that the total flux is nothing but q by epsilon naught as per Gauss's law. So therefore, through the curved surface, that's my question. Okay, I have to find out the flux is whatever is the total flux, that is q by epsilon naught, minus whatever is the flux coming out of the phase 1 and phase 2. So phase 1 and phase 2 is q by epsilon naught into 1 minus 1 by root 2, right? So this is the total flux. Okay, then this is the flux coming out of 1 and 2, and this is 1 plus 2 plus 3. So that means this side we are going to get the flux coming out of the third surface, curved surface, right? So if we do that, q by epsilon naught minus q by epsilon naught gets cancelled, minus minus will become plus, I'll be left out with only q by root 2 epsilon naught. That's the flux coming out of the curved surface. Okay, so the logic is simple. Why we are doing this? Because these kind of numerical problems might always be asked. Okay, simple. So the basic logic behind using Gauss's law is that you have the charge distribution and then you have to construct a imaginary Gaussian surface around it, which should be symmetrical, and from there you can basically find out your electric field. Okay, so that's important. So now what we are going to do is we are going to continue with the application of Gauss's law. Okay, we are going to find out the electric field. You understand the logic and how we are using Gauss's law. You can solve any kind of problem to find out the electric field where Gauss's law is applicable. Okay, so we are going to find out the electric field due to an infinite long uniformly charged wire. Okay, uniformly charged wire. Okay, so this is what we are going to check now. So imagine you are basically having a wire and it is uniformly charged, or uniformly the charges are getting distributed in this wire. So let's just draw that wire. Maybe I can draw it like this. Okay, this is a wire. Okay, and there are charges here. Now, I'm not saying that infinite long wire means it has to be really going up to the infinite point. Okay, I'll tell you what exactly it means by infinity. Okay, suppose you have a very small ant on this blackboard. For that particular ant, wherever it looks in all direction, it's going to see the board. So for it, the board is infinity, but actually the board is not infinity. So it depends from what distance we're actually measuring it. Okay, so that's the idea behind infinite long wire and so on. Okay, so anyway, you have this infinite long way. So let me just write down infinity on this side, infinity on this side, and you have to find out what is the electric field due to this at, let's say, a certain point. Okay, so let's say that certain point. Okay, let's say that certain point is at a distance r from its center. So this is the point that we are talking about. Okay, now what I want to do is I want to construct a Gaussian surface. Now this is a wire. So if I want to construct a Gaussian surface around this, if I want to construct a Gaussian surface around this, it has to be a cylinder. That's logical. And if I want to find it out at a point r, that means that this point r has to be at a distance r from the center. Okay, so maybe I can draw a better picture. If I take a line here. Okay, this is the imaginary Gaussian surface that we are drawing. Okay, so if we are having a line charge, the only surface possible around it which will actually be symmetrical in nature will be a Gaussian surface. So this is my Gaussian surface that we have. Now what will be the dimension of the Gaussian surface is totally my choice. So let me say that the length of this Gaussian surface is L. Okay, you have to find out what is the electric field here. Okay, but before we continue, we have to understand something, recall something here. What was my line charge density? Line charge density was nothing but charge, which is q, divided by the length. So if you are considering an infinite charge, we don't know what will be the total charge, but we know that per centimeter how much would be the charge. Per centimeter it will be q by 1 centimeter, right? So per centimeter we know how much is the charge. We don't know what is the charge in the entire thing. Okay, but if you want to know the entire charge, that is also possible. We can write q is equal to lambda into whatever is the length. So in that way we can use this concept of charge density. Okay, a linear charge density in this particular problem. So let's try to solve it. So what is our Gaussian surface? This cylinder. So whenever you are going to find out the flux, you're going to find out the flux through the Gaussian surface. So let me write down this phi, and the phi we are going to do it for the cylinder, the flux through the cylinder. So there are three surfaces which is actually around the cylinder. The first surface is this. Let's mark this as 1. The second surface is this. Let's mark this as 2. And the third surface is this part. Okay, so this is something which we have already seen in the last slide. We're talking about the cylinder. Now we have got three surfaces here. Now as I said, if this is my charge, the direction, if you take a very small area, let's say we are taking a small area here. Let me just drop this number surface and write it down somewhere else. This is my third surface. This is my very small area, and the direction of this area vector is this direction, dA. Remember, the direction of the area vector will always be perpendicular to the surface. So if you're considering this surface, the direction will always be in this direction, dA. If you're considering this, it's always going to be outwards as well. So this is dA. So this is dA, this is dA, this is dA. But the charges are distributed like this. That means the electric field is in this direction. The electric field is in this direction. So this is my electric field. So electric field in this direction for this also and for this also. So you see, for this also the electric field is in this direction. For this also it is in this direction. So that means in this case theta is equal to 90 degree. In this case theta is equal to 90 degree. But in this case theta is equal to 0 degree. Now if you want to find out what is the flux throughout the cylinder, coming out of the cylinder, we have to consider these three surfaces, phi 1 plus phi 2 plus phi 3. And when we are considering something as phi, it means that this is nothing but E dot dA, means E dA cos of theta. So we know what is theta. So theta is 0 for the third surface. That means cos 0 is 1. But for the first and the second surface, theta is 90 degree. Theta is 90 degree. And theta 90 degree means phi 1 is 0. Phi 2 is also 0 because cos 90 is 0. So that means the only contribution for the flux is nothing but phi 3. It's coming from the third surface. So that's simple, right? So what we can do is we can try to simplify this. We can say that a small flux would be E dot dA, and the total flux would be the integration of this. Okay. Obviously, we are going to consider it to be a closed surface. So E dot dA. Angle is 0, cos 0. So I can simply write it down as a scalar, which is E dA. But the electric field is uniformly distributed. Whatever is the field here, same is here, same is here, same is here, and so on. So that means the electric field can come out of the integral sign, and I can simply write it down as this dA. Okay, that's important. But by Gauss's law, this flux that we are talking about is equal to nothing but the total charge inside. Okay, let me write it down as In inside divided by epsilon naught. So statement is already there. Okay, so let me just write this down here. E closed integration dA is equal to q in by epsilon naught. Now area, look into this. This is a cylinder. You have to find out the area of a cylinder. If the radius is r, let's say the radius is r and the length is l, we know what is the area, total area. dA is a small area, total area of the cylinder, we can easily find it out. This would be nothing but 2 pi r l. Remember area, r into l, meter square area, right? Fine. Is equal to q inside by epsilon naught. But what is q? Q inside is nothing but the charge density multiplied by length, if you use the concept of charge density, linear charge density. So it is lambda into L. So what we can write down in place of Q in is lambda into L divided by epsilon naught. This takes care of the length. This takes care of the length of the wire. Okay. So please remember, when we say infinity length, it is only applicable when this r is small. If this r is very large, this infinite length will lose its significance. So we do consider that. Okay. So what we do is we can cancel out this L and this L, and that means our electric field E is equal to lambda by 2 pi epsilon naught r. A very important derivation. Why I'm deriving it today? Because I think if you understand this derivation, you can solve different kinds of problems using Gauss's law. Okay. But here we also see a very important conclusion, that this electric field that we have is inversely proportional to r. So a lot of time, a lot of trick questions being asked, that if you plot a graph between the electric field and the distance, how will it look like for, let's say, a infinite wire of charge. So I can write down electric field on the y-axis because that's the dependent variable. It depends on the distance, and distance is the independent variable. It is inversely proportional to r. So we'll basically have a curve like this. And definitely the slope is not going to be too high because it's proportional to r and not inversely proportional to r square. So if we draw this, it will be something like this. So we draw the graph. Okay. So there might be questions that will be asked. How will the graph look like? And so you should be answering it in this way. That's important. So the next thing that we need to do is electric field due to a cylinder. Okay. The electric field due to a cylinder. Electric field due to a cylinder. Now, if you want to do the electric field due to a cylinder, just a second. So what happens is if you are actually drawing a cylinder, you know, you can have different regions of the cylinder, and the cylinder at the same time can be of different types. Okay, so let's write down one thing. 10 minutes. Let's do one thing. uh, Write down the different kinds of cylinders that we can actually have. Okay, you can have different kinds of structures. Let's write down number one. It's a solid conducting cylinder. It can be possible. We can actually have a solid conducting cylinder. Very important. Okay, these words, and I will tell you which one you should remember. And there are different techniques to solve. There are two techniques for the cylinder. First is we're considering a solid conducting cylinder. Second, it's a hollow conducting cylinder. So I hope hollow and solid it's clear. Hollow conducting cylinder. So hollow, nothing is there inside. Solid, there is something inside. Okay, it's not hollow. Or and the third one is hollow non-conducting cylinder. Non-conducting cylinder. Okay, so the technique for finding out the electric field for all these three cases are the same. Okay, same technique. Please remember this. So in exam they might confuse you, ask you any kind of questions. You can tell They can tell you it may be a hollow non-conducting, it might be hollow conducting, or it might be a solid conducting cylinder. The technique will more or less remain the same. On the other hand, if someone tells it's a solid non-conducting cylinder, then the technique is different. Okay, solid non-conducting cylinder. This is different. So we're going to do two techniques. This is the first technique and this is the second one. So don't get confused. If you understand this logic, you'll see that they might ask you conducting or non-conducting, you can easily do it. Now let me tell you what is the basic difference between conducting and non-conducting. What happens in conducting is, okay, what happens in the conducting cylinder is that, or the hollow cylinder, or the hollow non-conducting cylinder, the charge will actually get distributed on the surface. If we are basically having the cylinder like this, the charge will always get distributed on the surface. It will never be at the center or somewhere inside. Okay, that's very important. Okay, it will always get distributed on the surface. Even it might be a solid conducting cylinder. Hollow, though, obviously there is nothing inside, so obviously the charges will be at the surface. But if you're considering even a solid conducting cylinder, the charges will always be on the surface. They'll never go inside. Okay, but on the other hand, if you're basically considering a solid non-conducting cylinder that is not conducting in nature, the charge will actually get distributed within the cylinder. We are basically considering just even distribution, evenly distributed in the cylinder. So that is the basic difference. So here you have to use the concept of volume. So volume charge density will come into picture here. But here we're more or less talking about the surface only. Only the surface charge density is important in this particular case. Okay. So solid conducting, hollow non-conducting, all for all of them, the images would be the same. Okay. So what we do now is, let me just draw one image here for our conducting cylinder. So maybe I can draw a cylinder like this. Okay, I should have drawn it a bit larger, but anyway. Okay, this is my cylinder. Okay, and let's write down some parameters for this. Let's say the radius of this is capital R. Okay, and let me just bisect this cylinder like this. Okay, bisect this cylinder like this. Okay, and we want to find out an electric field at any point inside the cylinder, maybe here. So let's say this particular distance that we are taking is small r. Okay, so we know that whenever we are going to find out electric field at any particular point, we basically have to construct a Gaussian surface. So considering this particular point, we are finding out the electric field here, right? And we know it's a conducting sphere or cylinder or a hollow cylinder and so on. That means the charges that we have are distributed here at the surface, okay. And let's say we have to find out what is the electric field at this particular point. So we are going to draw a Gaussian surface like this. We are going to draw a Gaussian surface like this, which is symmetrically distributed, okay. And we want to find out the electric field inside the cylinder, okay. So the idea is, point number A, inside inside the cylinder. Inside means this small r is less than capital R. That's the idea behind inside. Okay. So if you again look into the Gaussian surface, there are three: first surface, second surface, third surface. So if I want to find out what is the flux, it will be across the first surface, the second surface, the third surface. I'm not repeating this. We know that phi 1 will become 0, phi 2 will become 0. The only thing that survives is phi 3. Okay. But now what we can do is, we know what is my flux, that is E dot dA. This is a cylinder, so dA means area means 2 pi r l. Yes, this r is this r, cylinder radius of the Gaussian surface. Okay, that's very important. Is equal to the charge enclosed by Gauss's law. Phi is nothing but the charge enclosed or inside divided by epsilon naught. But if you look inside the Gaussian surface, since this is a solid conducting sphere or a hollow sphere cylinder or a hollow non-conducting cylinder, the charges will be at the edges. There is no charge inside. This is an imaginary axis, no charges inside. That means the charge enclosed is 0. So this is 0 by epsilon naught, which simply means that the electric field inside is always 0. There is a very common question. If you are basically considering a conducting sphere, cylinder or sphere, whatever, if you are considering a conducting sphere, what will be the electric field inside? The answer is always 0, and this is how we prove it. Okay, you can always show it in this way. Okay, the second case that we have is outside. So obviously we can find out what is the uh, field outside. Okay, so for finding outside, what we have to do is, we can take this r, which is greater than capital R. Okay, and we can again construct this. So maybe I will do a quick construction here. This is my cylinder, and the charges are distributed on the surface. I have to find out what is the electric field at a certain point r, which is outside this sphere. At a certain point, let's say this is the axis, a distance r. So again I will do the same thing. I will construct a Gaussian surface, something like this. It will be r from this side also, and this side also it will be more or less r. So I've drawn then constructed the Gaussian surface. Now look here, this Gaussian surface is enclosing this cylinder, the blue line. Okay, so that means it is enclosing the charges. So that means this cannot be zero. So now if I want to find out what is the flux, this would be again phi 3, phi 1 and phi 2 will more or less become 0. So phi by Gauss's law is nothing but the charge inside, enclosed or inside, divided by epsilon naught is equal to E into 2 pi r L. Please remember, whenever we are talking about E dot dA, that area is nothing but the area of the Gaussian surface. So Gaussian surface radius is r, so that's why it is small r. Now we have to find out what is the charge enclosed. Now for finding out the charge enclosed, we are going to use the concept of charge density. So if you remember, it's a surface, so it's a surface charge density. It is nothing but charge by area, so Q inside by area. But where is the charge? The charge is not on the Gaussian surface, the charge is here. So that means we have to consider the area of the blue cylinder inside. Okay, so that means this would be Q inside divided by area of the blue cylinder. The area of the blue cylinder is 2 pi capital R into L. Please remember this, don't get confused here. Length, I'm saying both same, both Gaussian surface in the cylinder, but when we are actually looking into the charge density, the charge is only distributed the charge is only distributed on the inside than the real cylinder. Okay, so that means if you want to find out what is the charge inside, it is nothing but 2 pi capital RL into sigma. That's my Q in. So we can replace it here. That means E into 2 pi small rl. Don't mix up small r and capital R, is equal to 2 pi capital RL into sigma divided by epsilon naught. Let's do some cancellation. 2 pi gets cancelled with 2 pi. L will get cancelled with L. Okay, and then we can find out what is my electric field. So if you look here, my electric field E is equal to sigma by epsilon naught on the right hand side, and here I've got capital R. This side only small r survived, so this is small r. So this is the electric field inside or outside the cylinder. Okay, for this actually we have a very graph we can draw. We can actually construct this graph. Let me just do this quick construction. Okay, we can again construct the graph between electric field and distance, and we can see there are two distances here. So let's say this is my cylinder, this is my cylinder, and let's say this is the edge, so this is my capital R. Okay, so you can see here, if we go inside, this is electric field. Okay, this side is electric field and this is my distance R. So if we are inside, the electric field is 0. Okay, let me take a different color. The electric field is 0 inside, the electric field is 0 here. But as soon as we come on the edge, means small r is equal to capital R. You can see here, you can replace it, small r is equal to capital R. This r and r will get cancelled. E on the edge, let's say, is equal to sigma by epsilon naught into capital R by capital R is sigma by epsilon naught. So that means at the edge, the electric field is maximum. So the electric field will suddenly jump at the edge. Okay, and then as soon as it crosses the edge, see again it becomes inversely proportional to R. This capital R is fixed. This capital R is a constant because that's the radius of the cylinder, so that cannot change. So the only thing that changes is this distance. So this again is nothing but, we can see E is inversely proportional to 1 by R. So that means outside it will again be like this. So outside the nature is like this, and inside this is the nature. If someone asks you what is the maximum field, it is sigma divided by epsilon.